Yes, thank you very much. I am trying to share my screen.
You should be allowed to now, I think.
Yes. Good. And you can all see it? Okay, thank you very much for the introduction. Yes, my name is Christian Kallesøe. I'm the director of our Center for Functional Materials here at DTI. And I'm going to talk today a bit about how we try to bridge the role between academia and industry and work as a non-profit RTO here in Denmark. Just a short introduction to our institute. It was founded more than 100 years ago, which makes us one of the oldest RTO in the world. We are approved by the Danish Minister of Higher Education and Science as an RTO. And back in 1906, when Gunnar Gregersen founded us, it was much about how that we need to position ourselves where we envision that our help is needed. And that is also still how we work today. We try to be there where we expect, especially the Danish industry, will need our help. To illustrate a little bit how we work, I'll just make a very short breakdown of our turnover, which just to show that we have mainly what we call commercial activities, where we work directly with companies, both Danish and international companies. But we also have a fairly large amount where we do research and development projects and activities. And that means that we right now have almost 500 R&D projects at the Institute, a lot of partners, a fairly large amount of budget. Our efforts at the Institute is divided into 5 divisions. So we have a division for food and production, building and construction. Then we have materials, where my center is placed together with 500 centers, all centers working somewhat with the P2X technologies also. We have a division for environmental technology and for energy and climate. And all these, this broad, all these areas that we work with also gives us a possibility to support a large amount, almost the entire Power-to-X value chain, for especially Danish companies. So we support startups, new product development. That is especially what we do in my center, trying to assist with the technology development, material selections, and so on. We do a lot of testing and validation, both to see if we meet performance, but also in terms of certifications. We work a lot on scaling and conversations. So how do we bring something from lab scale to pilot scale to full scale production? Then we support technology suppliers in terms of development, validation, technologies. We support plant developers, operators, and off-takers, also how to work with these new green fuels, how to adopt them. And that brings us to what kind of more specific service you can say we do. It's a lot related to the hydrogen, green derivatives. So we are experts within electrolysis, plant designs. We work a lot on materials and process optimization, especially in my center. We work on resource optimization, both with excess heat and water, but also how to integrate these systems in the larger energy grid. And then we work, as I said, on testing, validation, and certification. All of this we do together with companies, and this is also work that I cannot go more into depth with. But what I can go more into depth with is some of the R&D activities we have, where we work also a lot with companies. That's all really the central part of our activities here. And we gain knowledge ourselves, we gain competences, and also help solve the problems of various companies. So before I move into that, I'll just present my center just very shortly. So my center, we are approximately 30 people, working both within microanalysis, so that is electron microscopy and stuff like that, where we work directly with companies. They come in with a production error, contamination, maybe some development work. And then we have a section working with energy materials, which is the most relevant for the talk today, working with fuel cells, electrolysis, Power-to-X technologies, ammonia, and also battery material recycling. And then we have a section working on materials for electronics and integration of smart wearables. So moving into our R&D work, we have in our center a lot of projects going on. It's the 3 projects in the middle that are most relevant for today, which also means that we have a large network in Europe, and that is really what we try to do when we work with Danish companies in projects, is to bring them out into these larger consortiums and bring them into contact with the network that is needed to solve the challenges. Our P2X projects can all be related actually to the ammonia value chain right now. So we work with electrolysis technologies. More specifically, this project was about PEM electrolysis, where we develop new catalysts, try to reduce the use of critical raw materials, and also see how we can recycle these materials. Then we have a project running right now on how to convert hydrogen into ammonia in smaller systems, so decentralized production, and where we work with both the materials, but also on prototyping on the technology. And then actually in this middle area, we also have another project on almost the same subject that is starting up right now. And then also we have a project where we work on how to utilize the ammonia as a green fuel, how to retrofit ship's engine. So for example, 4-stroke engines, so you can combust ammonia, you crack some of the ammonia into hydrogen, so you get a mixture that has a better burn value. And then what kind of mixtures do you need to have the best utilization in the engine? So we work both on the cracker and we work on the engine flow. But for today, I'm gonna go more into depth with Recycleize. That is about electrolysis. I can just say, so why do we work with these projects? So it's first of all for us to gain knowledge, to gain competences, so we can develop new services for the Danish and international industry. But it's also to work directly with companies, having maybe some larger projects where we can really go into depth with some of their problems and bring them out into larger networks. Going deeper into Recycleize, this was about developing materials for hydrogen production, so PEM electrolysis. PEM electrolysis is you can say, one of the three main electrolysis technologies. Why we work with it is because we like to work with these smaller systems. What you also saw for the ammonia is about decentralized ammonia production. And PEM electrolysis has, first of all, a dynamic operation ability. It's a somewhat smaller footprint. You can work with high efficiencies. You can work at higher pressures, and you can get very high gas purges out. It only uses clean water, but of course, the main disadvantage is the use of critical raw materials. It's simply very, very expensive materials to work with. So the goal of this project was to really try to see, can we lower the price? Can we develop catalysts that has a lower usage of iridium and ruthenium? And that is also the objective, to work on the catalyst, but also to establish a recycling scheme to look at how to recycle the materials and utilize them again. That's also the concept. We work on the catalyst production. We look at both the active sites, but also how to utilize them on support structures, so we can again increase the activity and lower the usage of critical raw materials. We look at how to integrate them into, first of all, make inks, but also integrate them into electrodes, into membrane electrode assemblies. There's a huge optimization work going on here to optimize and to utilize the enhanced activity we have from the catalyst development. We integrate them into a stack, look at how it performs in a stack, and of course there's also a big balance of plant to develop here. And then we look at the end of life, how to do automated disassembly, and also how to recycle materials and use them again. The consortium you can see down here to the right. So one of our big competencies in the center is that we can do really fast material screening. So we have various reactors for nanoparticle synthesis, both large batch reactors. Here we use these, what we call flow reactors. So we have several reactors where we can go from lab scale to pilot production, you can say, producing very small amounts with fast outcomes, so we can change a lot of parameters in very short time, and we can really do a lot of optimization of the materials. And then we can also go into higher pilot production mode, you can say, and produce for these materials maybe 0.5 kilo an hour of nanoparticles. We work at very high temperatures and pressures, which gives us some advantages in terms of the control of the particles we get out. And then I mentioned that we worked here on supported catalyst. And why do we do that? It is fairly well known for fuel cells, where you have, for example, platinum and ruthenium on carbon particles, and why we use it is if you don't use supports, then you have a very low surface to volume ratio. It is really the bulk of the catalyst materials that conducts the electrons. And that gives you a poor utilization of your expensive materials. But if you can synthesize them, or you can place them on support structures, then you can have the support particles to conduct the electrons. They can also stabilize nanoparticles. You can make your expensive materials, the catalyst particles, smaller. Your support will probably not be as expensive as the catalyst, and then you can have a better utilization of your catalyst materials. And that brings us to the catalyst support, which was done in cooperation with Fraunhofer Institute in Germany. We need a support structure that has a high surface area, high conductivity, and also a high electrochemical stability. And the last part here is also why we cannot use carbon structures, simply because they corrode under these PEM operating conditions. What we found is that the most promising materials, both in terms of these three demands, but also in terms of reproducibility and how to scale it up, is antimony doped tin oxide. Especially when we synthesize it ourselves, we can get high conductivities, not as high as carbon, but in the same vicinity. And we can also get fairly large surface area, again, not as high as carbon, but much higher than all other, both commercial and self-made structures. And that brings us also to the core of our work, where we synthesize particles on these supports. A lot of different particles were tried. We can do this flow synthesis, where we can have support particles in one pump, we can have precursors in the other, and we then heat it up and develop these particles in a very short time span. Temperature, pressure we can control, and therefore we can also control the outcome of the particles to a very fine degree. And what we then developed was iridium with ruthenium alloys on support, and I was going to skip to this directly. What we see is that just from utilizing support, we can increase the activities of these materials quite substantially, also compared actually to commercial state-of-the-art supported catalyst. But actually, by introducing a small amount of nickel during the synthesis, we can obtain like a semi-amorphous structure with a mixed rutile and hollandite structure, and that means that we can really increase the activity of the catalyst while maintaining, actually, because that is leached out afterwards, while maintaining the activity of the catalyst. This activity we need to also utilize in the MEA structure. So how do we actually how do we make sure that this boosted activity is also reflected in the MEA, and then how can we then decrease the amount of catalyst that we use? A lot of work together with our partner Blue World Technologies in Denmark was done on optimizing the amount of ionomer, which ionomer. All sorts of parameters were optimized in the end, coming up with a MEA structure that we integrated in a stack. And then the stack was then tested in the system you see here to the right, down in Austria with our partner Hysenta. Just to go briefly through it, the stack showed stable operation. If you look at the graph, don't focus so much on the green one. That was a first try, or only halfway through the project. But if you compare the purple lines and then the orange lines, that is a commercial stack with a higher amount of PGMs, and then our stack, which just showed that we actually made both a material, a MEA structure, and a stack that performs better than the commercial alternatives with a lower amount of PGMs, with a high gas quality. And all in all, we optimized this system, which was based on model-based control, so we can really reduce the amount of sensors. I will not go so much into depth into this part of the project. And now I can see I'm running out of time. So very briefly, we also looked at the recycling scheme, how to dismantle it, how to separate the catalyst and dissolve it, how to distillate it for ruthenium recovery, refine it, get all the different materials out into different salts that we can then utilize, and then we demonstrated how using these salts we can actually create catalysts with just as good activity as a commercial salt, a precursor, and with a recycling efficiency of over 90%. I think I've used my time, so thank you very much.
Thank you, Christian, so much. Of course, we'll come back to this in the panel discussion, depending upon what are the open questions at time. I'd like to really thank you. I have not seen any questions in the chat yet. Oliver, if you confirm that is the case. And
I have not seen anything either.
yes, then we can move to Professor Mondar next.